All right. Thank you, Mohammed, and thank you all for being here. It's a pleasure to welcome you all to my hometown. I hope you enjoy the conference. Today, I want to talk a little bit about the work that we've been working on for about a year. It's called mapquik, and it's a new HiFi mapper that's efficient in order to map long, accurate reads. So long read sequencing, we know it, we do it, and it's been a particularly great year for long reads. Nature called it Method of the Year, and this is in large part due to the completion of the human genome by the T2T consortium. And thanks to their work, we now have a telomere-to-telomere gapless assembly, the first complete assembly of a human genome. And of course, being able to map long and accurate reads plays an important role here in improving the draft assemblies for the complete assembly, to achieve the complete assembly. So what does the future hold for long-read mapping applications? Ideally, we would want more T2T or near T2T assemblies and resolve haplotypes on these assemblies. We would want more metagenomic and pangenomic assemblies. And of course, we would want SV calling and phasing to be accurate, and also improve on transcriptome assemblies and transcript-specific quantification, and also discovering isoforms. But maybe most importantly, we would want to have more than one reference genome. And with human pangenomics, improving the performance of long, accurate read mappers is paramount. And on top of all this, everything is moving to the cloud. So if we want to have our long-read mappers work in the cloud and make it available, we would need to balance runtime costs and memory costs as well. So these days, we have a couple options for mapping PacBio HiFi reads, or long and accurate reads in general. So we have Minimap2. It is used everywhere in many, many applications. It is considered the informal state-of-the-art. We have its CPU and GPU accelerated versions, MM2 Fast and MM2AX. We have Blend, which was earlier presented by John over there, using a new kind of seed called stromers, and also a fuzzy hashing technique. And we have WinowMap2, which uses minimal confidently alignable substrings to guide the seeding step. And it also uses a minimizer scheme, seeding, extension. And this mapper was used in the CHM13 assembly, the first complete assembly. So going back to our goals, in the case of human pangenomes and near T2T assemblies, it turns out that our options these days end up being extremely slow and memory intensive. And these runtimes are also not looking very promising if we want to make sequencing to diagnostics readily available in the future for clinical applications. And I'd like to make a small point about moving read mapping to the cloud here. Let's say you want to compute the cost of mapping a set of HiFi reads 30x with 1% error rate to the CHM13 reference. And here is the smallest AWS instance that can do that. And it's around 34 cents a CPU hour. And mapping 30x HiFi reads with Minimap2 takes around 8.5 CPU hours. So that's $3 spent just for mapping a single read set to a single reference genome only one time. And considering WinowMap2 is even slower, it ends up being more expensive at around $79. So this is something that we need to take into account if we want cloud analyses to be possible with long read mapping. So looking at Minimap2 as a case study, we want to kind of figure out what can be improved here. So it uses minimizers, which are specially selected k-mers There have been a lot of talks that mention minimizers throughout the conference, and it uses a seed and extend strategy. Let's say you have your reference, you obtain a set of minimizers. These have the smallest value within a window of a certain length. And we would build a reference minimizer index storing the sequences and the positions of these selected k-mers. So if we have a query sequence that we want to map to the reference, here's a sequencing error in blue here. We would do the same thing, but on the query, obtain minimizers, and we would then query the previous reference index using the sequences of these minimizers, and we get some matches. So let's say here, given the reference index, these, maybe that's better, these k-mers found a match in the reference index, and here are their positions. So then we heard about collinear chaining. That's what Minimap2 uses. This is a simple example where we check if the query and the reference positions of the matches agree. So if they're collinear. Of course, in practice, it would use a dynamic programming formulation that ends up being more expensive, and I'll talk about that later. But here, their positions agree, so we would chain them and output the final coordinates. So that's kind of the general idea that Minimap2 uses. So what can be improved here? What are we doing, quote unquote, wrong? And I'm using wrong very liberally here. There's nothing inherently wrong with Minimap2. It's just there are some things, some observations that I'd like to make that could possibly improve Minimap2 here. So we find that long and exact seeds, like minimizers, are not quite adequate for mapping long reads because they lack the sensitivity needed. So for example, for CHM13, these minimizer seeds either have too many matches, so from tens to thousands between the range k equals 10 to 100, or too few for large numbers of k, so let's say k larger than 300. And Minimap2 has a default value of 19, k equals 19, meaning it has to go through hundreds of false matches for each read, and this costs a lot of time. So before I move on, I'd like to kind of take a detour and talk to you about our previous work on MDBGs. And this was also presented at Recom 2021, also on Self Systems, where we use what we call k-minmers as nodes in a de Boering graph instead of the classical k-mer formulation. So here's what I mean. So the classical alphabet we have has A, C, G, T, N as the letters. So here's an example k-mer in this alphabet. We use what we call a minimizer alphabet, where the letters we use are themselves minimizers. So they're themselves sequences of a certain length. In this case, we denote it as L. So in this example, we have a fixed set of minimizers that we pick before looking at the sequences. This set of minimizers are fixed. And given a sequence, we can just locate the minimizers by checking their hash value. And the alphabet we can write out as all minimizers of length L, this fixed set. And let's say we have 3 minimizers here, M1, M2, M3. These are some examples of the letters in that alphabet. And L equals 2 here. So a k-minmer would be just a k-mer over this extended alphabet. So it would be M1, M3, M2. So it turns out that k-minmers have the potential to be used as alignment seeds instead of k-mers. And here's what I mean. So here we plotted on the left, the median number of occurrences of seeds, both kinds of seeds. So in blue, we have regular k-mers. And in orange, we have k-minmers. And x-axis is seed weight, so number of nucleotides used. So for k-minmers, it would be k times L. And we plotted the median number of occurrences of these seeds in the CHM13 reference. So you can see here that the default value for Minimap2 has over 100 occurrences on average, or the median number is 100. Whereas if we use k equals 5 and L equals 31, the minimizer length 31, it has less than 10 occurrences. And you can see in general that the curve is less steep here. And on the right, we have the average number of reference locations if we only store unique k-members and query this index per read. So we can see that we're very, very close to a single candidate location on average. So a general strategy would be that if we index all unique k-members, and for each read, obtain the k-members and query this reference, we're very likely to find the right location really fast. So let's say, so that's exactly what we do in mapquik, which is our long-read mapper that uses unique k-member seeding. So if we have a reference sequence, we can obtain random minimizers and build our k-mers here. And now we can build an index of these k-members from only the unique ones that we see. So here, for example, we have 8 k-members, but note that we don't store x1 and x5 because they're the same k-member. So now that we have our seeds, and we have a much fewer number of seeds compared to regular k-mers now. So instead of using dynamic programming to extend these seeds, we can perform a linear time step where we extend each match maximally. So here's what I mean. Let's say you have the exact same query sequence, and we do the same thing, obtain minimizers, stitch them together, and get k-members, and then we query our reference index with the values of these k-members. Let's say these are the matches we've found. Some of them are missed, either because we don't store k-members that occur more than once, or because of the sequencing error. So now we can extend this k-member match maximally by checking the very next k-member and see if it matches the very next k-member in the reference. So we would want to extend a k-member match, we would want the matches to be consecutive in terms of list positions. So in this example, so we have 1 and 2 matching 3 and 4, which means they're both consecutive in the query and the reference. So we can merge them and just say x3, x4, which is a maximal k-member match. So those of you who worked in short-read mapping might recognize this. It's very similar to a maximal exact match, meaning that we extend it in both directions, but we do it in minimizer space. And then instead of doing a DP formulation for chaining, we do another linear time step, where after extending k-member matches maximally, we look at the match with the highest k-member count and only chain other matches that are collinear with it. So this is another linear time step where we only need to scan the matches and check for collinearity. It doesn't have a collinearity guarantee in terms of pairwise collinearity between among all the matches, hence the pseudo, but we find that it works well in practice. And I'll demonstrate by showing our evaluations. So we compared mapquik to these mappers here, minimap2, mm2 fast, minimap2, and blend, using 3 read sets. So one of them is a simulated CHM13 read set with 1% error rate, 10x, 24 KB mean length. Same for maize, the maize genome, except it's 30x. And we also use the most recent real HiFi read set from the Deep Consensus team. We ran mapquik with default parameters, all other mappers with HiFi mapping mode, and evaluated through path tools. And we specifically focus on mapping quality in the sense that we look at the highest quality, so reads mapped with the highest quality mapq60. And mapquik reports a mapq of 60 if the output chain satisfies a certain threshold, either in terms of score or in terms of length, and we output 0 otherwise. So here's the, my slides got messed up. Here is the results for the simulated CHM13 reference. This is the simulated 10x read set, and it's hard to see here, but the time is 18.6, and the speed up is 47.74x. So it maps 97.2 percent of reads, 2 wrong positions, and with almost a 50x speedup. And on real HiFi reads, with 30x coverage, we have almost a 40x speedup, and we have the second highest number of percentage of reads mapped after winnow map 2. And on simulated maze reads with 30x coverage, we now have a 400x speedup with near perfect accuracy, only 2 wrong Q60 positions, and again, the second highest percentage of reads mapped. So how am I doing on time? I guess I can quickly talk about what we do subpar in terms of, with respect to other mappers in challenging regions. We checked for concordance, and on simulated reads, we have a 99.8 concordance with minmap2, which speaks to the accuracy of mapquik. And on real reads, we checked the missed intervals, both by minmap2 and mapquik, and see if they intersect. So here we plotted the number of missed intervals and the percent of overlap. So we see that when it converges to 100%, less than 100 intervals don't have a 100% overlap with minmap2. And also, when we plotted by missed interval size and percent overlap, the median length happens to be around 10 to 50 kb. So both the number and the sizes of the missed intervals are quite small. And here's an illustration of chromosome X. You can see that the missed regions kind of agree. I mean, we seem to be doing better than minmap2 at Q60 in most, and they happen to be around challenging regions such as, centromeric satellites, segmental duplications, and then there are also some challenging regions that might be related to the performance of minimizers. So the next things that we're considering is making alignment, base level alignment, available as soon as possible, and mapquik can also be used as a first step before minimap2 or winnow-map2. Feed the easy reads to mapquik, and then run the rest with minimap2. Just get a runtime speed up. We want more mapq, a wider range of mapq scores. Sequence to graph alignment is possible. Maybe compression through alignment in the sense of alignment maps. In general, there are a lot of exciting directions. So that's all. This is mapquik, speedups of 40x to 100x, minimal loss of accuracy. I want to thank my co-authors, Ryan, Bonnie, Paul, Chris. This project has been very near and dear to my heart, and thank you all for listening. I know I ran out of time a little bit. I'm sorry, Mohammed. But here's a QR code. You can check the code on GitHub as well. Thank you.